All right, now that I'm sharing the screen, it makes sense to record the notes. Anyway, on Friday, correlation, we talked about shape, strength, and direction of correlation. We were looking at dots, and we were, trying to guess on how closely packed dots were to decide if they were moderate or weak or strongly correlated, and taking guesses is not accurate. Besides, if I give you a string of numbers instead of dots on a graph, how would you tell me if they're correlated or not? Well, we use Pearson's product moment correlation coefficient. That's a mouthful. It's an R value. We use the letter R for this. It is the correlation coefficient. In your IAs, should you do this kind of math, you will not say R value. That will hurt you. No, you will say the correlation coefficient. Or if you really wanted to get fancy, you could say the Pearson's product moment correlation coefficient. No. Yes. Now, a product moment literally means a product, which is multiplication, and moment in physics means like average almost, medium, kind of, where something is in the dead medium, okay? Or dead middle. Like a place where, say, a structure would balance. You call it the moment of gravity. It's where it's balancing. So it's usually middle, median for statistics. For a set of n data points, like 20 data points, 50 data points, 100 data points, you can list them all as x comma y's, because if you're talking about correlation, you're legitimately talking about how closely related two variables are. Okay, two variables. Gotta change cameras. So these data values will be listed as x comma y's, x1, y1, x2, y2, x3, y3, so on and so forth, all the way out to the xn comma ynth term. Well, the Pearson's product moment correlation coefficient is calculated by this bad boy right here. You see on top, we have the product of the distance between every term and the mean of the x's, the distance of every term and the mean of the y's. You multiply those, and then you add them. That's a lot of stuff. Now on the bottom, you got the same idea, but you're squaring both of those things. Then you're adding them, and then you're taking the square root. It's a lot going on here. As long as the math is done right, and be thankful, you will not be doing this by hand, your correlation coefficients, your R values, will land between -1 and +1. -1 is as low as it can go, +1 is as high as it can go. Can it be equal to -1 or +1? Yes, it can be equal to them. But if you're equal to +1, that is a perfect positive linear correlation. If it's equal to -1, that is a perfect negative linear correlation. And the only time that happens is when you're graphing a straight line. So if I give you y equals 3x plus 2, and you try to find the correlation coefficient between the x's and the y's, it would be a perfect 1, because they lie on a straight line perfectly. The sign, whether it's positive or negative, indicates the direction of the correlation. So if your R value is positive, that's a positive correlation. If your R value is negative, that's a negative correlation. The quote-unquote size of R indicates how strongly they are correlated. The closer to +1 you can get, the stronger the correlation. Now, if you're getting close to 0 on the positive end, you're getting close to no correlation, but it is still positive, so it's like weak. The closer you can get to -1, the stronger that negative correlation is. Of course, if you're getting close to 0 on the negative side, you have a weak negative correlation. Now, these boundaries for strong, weak, and moderate do have classic numbers associated with them. You do not have to have these memorized, though. If you are going to use terms in your IAs like weakly correlated or strongly correlated, I would expect you to pull from this table, this is known information in statistics, and use it in your paper. So positive correlation. It's considered a very strong correlation if it's between 0.95 and 1. It's considered a strong positive if it's between 0.87 and 0.95. Moderate is 0.5 to 0.87. Weak positive is 0.1 to 0.5. And anything between 0 and 0.1 would actually be considered really no correlation. They're not really related at all. And we use the exact same numbers, only negative for the negative correlations. And again, you don't have to have these memorized. They will be given to you if you needed it. A group of adults is weighed, then their maximum speed when sprinting is measured. So we have weight in kilograms across the top, and we have our maximum speed in kilometers per hour on the bottom. It says draw a scatter plot. Yuck, right? But to be honest with you, that's the hardest part of the homework, is drawing scatter plots. Okay, well, let's get a scatter plot going. Only positive x's and positive y's make sense. And what do we got going on my x's? These are weights. What are they? They go from, looks like the smallest one is 60 and the biggest one is 100. Okay, from 60 to 100. Picture not drawn to scale because who cares? Here's 60. Here's a hundo. And if I go by fives, how many tick marks is that? 6 marks? So 60, 65, 70, 75, 80, 85, 99. So 60, 65, 70, 75, 80, 85, 90, 95. Yikes, that was really bad. 65, 70, 75, 80, 85, 90, 95. That's better. Much better. And our weights, no, I'm just giving you our speeds. What do we go from? 17 up to the number 30? Picture not drawn to scale. 17 to 30. I could go by threes if I wanted to, right? It wouldn't be pretty, but it would work. So it would be 20, 23, 26. Wait, it doesn't make any sense. I can't go by threes. What am I smoking? I don't know. Not smart today, I guess. Ugh, I don't want to have to go by ones. It's 13 tick marks. Okay, going by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. There you go, you get it. Okay, it's just a scatter plot, okay? It's just a scatter plot. So we have 85, 26. Just going to be, what is this? Here's 90, here's 80, here's 70. So scatter plotting it away. And 85 to 26. It's like somewhere around here-ish. Just guessing at this point. 60 to 29, that's way up here-ish. This doesn't need to be perfect. 78 to 24. I don't know, that's like right around there. 100 to 17. That's way down here. 83, 22. I'm just kind of throwing these up there. 67 and 30. 79, 25. Was it 62, 24? Yeah. That's right around here-ish. 88, 19. And 68, 27. Last but definitely not least. 68, 27. That feels pretty good. There. It says use technology to find R for the data. Thank goodness we're using technology, right? Because we are not trying to use the Pearson's product moment correlation coefficient equation, that was a lot of words, by hand. We don't want to do that. Instead, we will go to handy dandy graphing calculator, and thank goodness for technology. So just like before, this is going to be in stat edit because you are trying to make new lists. Now my lists aren't clear, so I'm gonna go ahead and clear L1 real quick, just reminding you, go up to L1, hit clear, hit enter, and yay, list is cleared. I'm gonna make X1 my weights, and the nice thing is, we talked about this last week, they don't have to be in order. So thank you, TI. The only thing you have to do is make sure that you don't fat finger your keyboard. Make sure that you typed it perfectly. It's worth the extra moment to go through the list and double check your numbers to make sure you didn't screw that up. So it really, really stinks when you don't get credit for a question because you didn't pay attention to what you typed. $88.68. All right, and then L2 are your Y values. Now last week when we were doing this stuff, we weren't doing two variable statistics because we didn't have two things that were changing. Now we did have x's and we had numbers in the y in the L2 column, but they were not y values. They were frequencies or cumulative frequencies. See, those aren't a separate variable. That was just you adding up the one variable you had. This time we have two different things that could change. So this is going to be in two variable statistics. So you go to stat, calc, two variable statistics.
Beautiful.
It has what's the x list, what's the y list. You do not have a frequency list, so leave it blank. And then calculate. And it spits out a whole bunch of stuff. Now guess what? Because it's been so long since I did it, this is not what I needed you to do. Because I forgot what I was doing. I forgot I was doing linear correlation. Well, anyway, that's useful to you in college. What you were supposed to do was stat, calc, linear, linreg, linear regression. Sorry, not two variable statistics. That's outside the realm of this curriculum, my B.
Why?
Why what?
Why don't we learn about it?
Because this is IBSL, not IBHL.
What makes it HL and not SL?
Two variables instead of one variable is what makes it HL. Anyway, we're going to do linear regression. And I would like you to notice that number 4 and number 8 look remarkably similar, don't they? But which one looks like slope-intercept form? Number 4, AX plus B. That's the only one we use. So you hit enter on number 4, and still the same thing. Now this one is actually pretty cool. You can store this as something. I'm trying to remember. You can name it, and you can ask the calculator to graph it for you, which is pretty cool. I can't remember how to do that though. I think I can go to vars. You don't have to do this. Let me see if I can just do it real quick. Vars, yvars. Yes, it's a function. Let's call it y1. True. Okay, and I'm gonna hit calculate. Now it just spit out an equation for me. But, did anybody else's calculator give them more information? You see, what you wanted here was a lot more information, because on here it should have given me the R value as well. So what that tells me is that our stat diagnostics are turned off. Now I have to figure out how to do that, and I don't remember how. So let's go to mode, stat diagnostics in mode. So scroll down to stat diagnostics and click it to on. I don't know why mine is off, but it is. It's good video notes for anybody at home whose calculator did not automatically have it on. Let's try it again. So stat, calc, linreg. We do have to restore it. You don't have to do this storing thing. I'm only doing that so I can graph it. That's the only reason why I'm doing it. Just because it's... I don't know why you would want stat diagnostics turned off. No clue.
Wait, so we should restore things?
You don't have to. That's only if you want to graph it.
But will we want to graph it?
Let me show you why I'm doing that. Okay? Do you have a question for me?
Where'd you get Y1?
I clicked vars, and then I scrolled to yvars, and then I hit enter on y1. Now I'm going to hit calculate and hope, fingers crossed, there it is. Woohoo, worked that time. Notice we have an R value and an R squared. Oh, can't just say I'm confused. What are you confused by? What do you mean I don't know? Ask me. Damn thing is empty. Anyway, R. In this class, we do not use R squared. You can use R squared in higher stat courses, yes? You don't know how to turn on stat diagnostics on an older operating system? Right, it's not in mode. You have to go, I can show you here in a little bit, okay? Let me finish notes and I'll show you how. I can't describe it, but I can do it. It's like I have muscle memory of it. I just don't remember what the commands say. Great, so our R value is to 3 sig figs, negative 0.813. There we go. That was a lot of fun, wasn't it? Negative 0.813. So then it says to describe the correlation between weight and max speed. Well, that number, negative 0.813, we know it's negative, and it falls right in here. It falls between negative 0.5 and negative 0.87. So we would say that this is a moderate negative correlation. So because we are negative 0.87 is less than R, which is less than or equal to negative 0.5, we have a negative moderate correlation. No, you don't have to memorize those numbers. You don't have to memorize those numbers, thank goodness. Luckily, right? So that is legitimately everything from that part of the notes. That was it from that section of the textbook. So when you go to do that homework, the hardest part about it is drawing scatter plots. And you saw how much effort I put into it. Okay. You'll never be asked to make a scatter plot on an IB exam. So don't stress out about that. Can we move to the next part of the notes without anybody freaking out? What's he doing? You making a TikTok over there? Huh? We good?
No.
Okay. Well, then we'll move on to the next set. Line of best fit. So you see that equation that it gave me, that AX plus B? That was what we call the line of best fit. But it's got a stronger name than that, and I can't remember the whole name of it. It's called the regression line of fit or something like that. The point is, the line of best fit can only be found using technology or at this level. And if you're interested in how to find line of best fit by hand, you are welcome to take a course called regression in college if you don't like yourself. At this level, we will just use technology. We don't need to know how they did it. So before you actually can use technology, you have to be able to find a line of best fit by eye is actually what it's called. And the way we find a line of best fit by eye, meaning your EYE, your eye, is first figure out what X bar and Y bar are. So you have to find the average of the X's, you have to find the averages of the Y. This is called the mean point. Now the mean point does not need to be within the data set. You just find it. And you would add this mean point to your scatter diagram, your scatter plot that you made. Then you would draw a line that goes through the mean point, and you try to get it as close as possible to other dots as possible. And you just make sure you go through one more dot. Because now you have a line that goes through two known data points. And you could do algebra 1 to find the equation of that line. That is called the line of best fit by eye. Well, because you have the option of going through basically any other point you want other than the mean point, there's going to be a lot of different correct answers for that. I have never seen an IB question where you found a line of fit by eye, ever. Now, they might give you a line of fit by eye and ask you some questions about the image to analyze it and things like that, but to actually find it, you don't have to. Are you going to have to? Yes. So we can use our line of fit by eye to estimate values that's within the data set. So as long as you plug in an X that's within the range of your data set, you can use your line of fit to estimate a Y value. This is called interpolation. Now, you can use your line of fit and plug in an X value that's outside of the range to estimate a Y value. Like say you were trying to predict the future or something. But this is called extrapolation. And by definition, extrapolation is not considered statistically viable. The accuracy of extrapolation actually depends on one, how linear was the data, and an assumption that the linear trend will continue. And, whoops, dropped my paper. And what was the other? And two, it also assumes that the data can go on forever. But not all data can go on forever. You know, imagine you have a straight line with negative slope. Eventually, it's going to hit the x-axis, right? And once it dips below the x-axis, you're talking about negative y values, and in the real world, those negative y values don't really make sense. So you have to be careful. So basically, if you're going to extrapolate, be really, really careful. The one thing the book doesn't say is the further away from the pack of data your x value is that you're plugging in, that you're extrapolating for, the further away it is, the less reliable that extrapolation will be. Kind of like how the county uses your reading scores from 2 or 3 years ago to predict what score you're going to get on the IB exam at the end of your senior year in mathematics. You see, this is extrapolation, which in statistics is actually not allowed. But they're going to do it anyway to determine how good of a math teacher I am based on your reading skills. Okay? Also, be really, really careful. Predictions, even interpolation, meaning you're looking at x's inside your range, can only be done by plugging in x values. You may not take a y value and go backwards to try to figure out what x matched with it. That is not allowed in statistics. I think, and don't hold me to this, I think that's what the other linear regression command is for on the calculator, because it will give you a different line of fit. So you may only plug in x's. You may not use a y to predict an x. That is not how linear regression works. You can only use x's to predict y's. Cool with that? Okay. This isn't going to be fun. So on a hot day, 6 cars were left in the sun in a car park, meaning a parking lot. The length of time each car was left in the sun was recorded, as well as the temperature inside the car at the end of the period. So we have what, 6 cars? We have time in minutes, we have temperature in Celsius, because IB. Well, part A, you're going to calculate x bar and y bar. I went ahead and plotted the dots for you, so you didn't have to make the scatter plot. I know, right? Actually, so I didn't have to make this scatter plot. But we are going to find x bar and y bar. We can either do this by hand, or we can ask our technology to do it for us. You vote that one? Okay, well, that one, let me grab my chair. This time, do you remember how we got x bar back in the day? By using one variable statistics? I'm pretty sure that 2 variable statistics will give us x bar and y bar if we use 2 variable statistics. Now, I can't see this table anymore. I don't actually have these notes, so I'm going to need you guys to tell me what the table says. So stat, edit, I'm going to clear both my lists. Okay, and if someone could hit me with the x's, that would be great. 50. Yup.
25.
Mm-hmm.
40.
Yep.
15.
Mm-hmm.
45.
Thank you. And the matching y's?
47.
Mm-hmm.
28. 36. 42. 34. And 41.
Great. Stat, calc, 2 variable statistics. Fingers crossed, I've never done this before. There's XY, there's X list, there's Y list, and we're skipping frequency. Give it to me now. Hey, look, there's a X bar and there's a Y bar. Woot, there they are. So 2 variable statistics is good for finding X bar and Y bar. We have X bar is 30, Y bar is 38. So using technology, we have 30, 38. It says draw a scatter diagram for the data. Yeah, I did that for you already. I'm sorry? No frequency list. These aren't frequencies. So you just leave it blank. And if there's something there, just clear it off the frequency list. It says locate X bar, Y bar on the diagram and draw a line of best fit incorporating 30, 38. So let's see, where is 30, 38? 30, 38 looks to be about here-ish. That looks good. And I want to draw a line through, I don't know, grab a straight edge. And I feel like going through the one that's right next to it would be best. Like this. That feels like that's the best one. Yeah, it looks like that. See, I'm trying to get relatively the same number of dots above it and below it. So which one was that? Was there one that's at 26 or 25 or something? What are the coordinates of that dot? Nobody's saying anything, so I'll go back up to the table myself. Now you get 25 comma 36. Yeah, so this one's at 25 comma 36. And we knew that our x bar, y bar was 30 comma 38. So what we need to do is we need to use, either we could use some algebra 1 and write the equation for this, and then we could plug in, or we could just use our line, since it didn't ask us for our slope or anything, and we could just use our eyeballs, predict how long it would take for a car's temperature to reach 55 degrees. Well, in order to do that, I would have to extend this line. Wow, unfortunately it's getting fatter, but 55 degrees is a temperature. So 55 degrees, and I'm going to draw a horizontal line at 55. That looks like 55. Wow, look at that. So this is, I don't know, this is somewhere really outside the data, isn't it? I mean, this is looking like, this would be like 90. So that, and this would be about 100. So I don't know, that's somewhere around the 93-ish mark. It's just an estimation. So x is time, right? So for part E, we're looking at like, I don't know, somewhere around 93 minutes. Is it minutes? Can't remember. Yeah, somewhere around 93 minutes. Hold on a second. Part D and part E. Oh, I skipped over part D. I'm sorry, that was part E. My apologies. Part D. Predict temperature of a car that has been left in the sun for 35 minutes. So let's use a vertical line for that one. 35 is about here. Temperature of that car is,
39.
yeah, I like 39. Why not? About 39 degrees Celsius. I'm still on vertical line. About 39 degrees Celsius. That feels good. There. Now part F asks us to comment on the reliability of our predictions. So for D, prediction of 39 degrees. How do we feel about that? Is that reliable or unreliable? And why would you say reliable? Yeah. But more specifically, why would we, this is reliable, but why would we say it?
Would it be because like you can see where the point, like the other points are?
Kinda, that's what he was saying. When you mean you can see where the other points are, what are we getting at here?
Because it's in the data set?
It's in the data set. It's interpolation, because this is within the range of the values. So this is reliable. And all you have to do is say reliable because interpolation. Now for the prediction of the 93 minute, I'm just going to go ahead and do this one, prediction of 93 minutes. And I want to talk about this for a moment. And then I'm going to have to talk to Mr. Donovan about this. Prediction 93 minutes. Reliable or not reliable, you guys would say? Not reliable, but why? Because it's extrapolation, and that's what the book says. But I 100% disagree with the authors on this one. And that's because in the old textbook, this was unreliable because it was a y value being used to estimate an x value, which is not allowed. I don't know why they have changed their views on this. Regardless, the answer is still that it's unreliable. But I will say that your authors have said because it is extrapolation. But the old curriculum said that you were never allowed to use a y value to predict an x. So we'll have to talk to Mr. Donovan and Mr. Lash about this, who are the other stats teachers, and see what they think about it, and I'll get back to you on it. Yeah.
Okay, so for this specific model,
Mm-hmm.
if you put 50 minutes or something,
Mm-hmm.
and theoretically,
You mean if we had, if
grow,
you mean if it was on as part of our data already, or we're trying to figure out what's happening at 50 minutes?
yeah, we're trying to figure out what
Okay, we're trying to figure out what happened. Mm-hmm.
But like the car stops getting hotter at a certain time
Yeah,
because it can't just continue to always.
exactly. It won't continue forever.
So, but the time is still continuing.
Time continues forever, yeah.
So how do you know if it's still like?
And that's why, okay, so that's why we try not to use extrapolation. Because we are aware that this car can get hotter than, we can at least get 50 degrees, right? Or no, 50 minutes. We know we can at least reach whatever that big old number was right there. Was that like 47 or 46 or something? We know that. And we do know what happens when we've looked at 50 minutes. So if you guess a time that's less than 50, then you know that the car should be somewhere below the maximum temperature we saw at 50 minutes.
Right.
But like you said, temperature can't go up forever. So at one point in time, it is going to peter off, and that is why extrapolation is dangerous. The closer you can get to the last value in the range, the more accurate your extrapolation would be, but it's still extrapolation. Okay? And because of what you just said, that's why extrapolation is not highly reliable.
Yeah.
Yes?
I think that's why they said both extrapolation and using the line.
They didn't say that.
I mean, in
I-
the last one.
Well, in the last one, they said they never. Yeah, in the last one, they said extrapolation is not allowed, and using Y's to predict X's is not allowed. But in this current book, it doesn't say anything about using Y's to predict X's, and I don't know why they removed that from the text. So I'm gonna talk to their stats people and see what they think. Is there more to this, or was that it? That's it. Awesome. Cool. We survived into the stats lesson. Woohoo!